So without much further ado, I hand over to my dear Daniela. Take it away.
Thank you, Alex, and wonderful that you have us here today. And I will also keep myself very short because the most important people are coming just after me. So it's wonderful that Mahsa, our current Herz fellow, and Anteneh, our current ZUKO fellow, will present their work today here at the cluster. The Herz and ZUKO fellowships are a tool from the Zukunftskolleg together with the university to encourage early career researchers from Africa, Asia, and Latin America to join us here on campus for 3 to 4 months with a short fellowship, but also stay affiliated to us for a whole duration of 12 months. And you actually will see that Mahsa and Anteneh have already left the Zukunftskolleg a couple of weeks back and are already back home, and probably have a lot better weather that we currently have. But today's focus will be on their research. And we also have current call for both fellowships for the ZUKO and the Herz, and they're actually quite similar. So the fellows, when they are at the Zukunftskolleg, are just benefiting from the same. But while the ZUKO fellowship doesn't require any prior connection of the candidate to the university, to the 13 different departments or to the clusters, the Herz fellowships, they have a very strong component of early contact per se. So there's a junior or a professor of the university who give nomination proposals for those Herz fellows. And it's actually quite interesting that we have at the cluster this year, one of each, one Herz and one ZUKO fellows. And with that, I already stop. I will put you some more links into the chat and be happy to come back to us. Current calls for the application close for ZUKO on the 15th, and for Herz, where all of you might still want to nominate somebody, on the 15th of March. And with that, I would like to now introduce Mahsa. It's very good also to see you, Mahsa, virtually again. Mahsa is a PhD candidate from Iran, and she returned, as I told you, a few weeks back. She has a very strong record at her home university. She's one of the best students there and won numerous awards as best student and as best master student. Her research focuses on graph coloring, but beside that, she's also looking into data mining, deep learning, and machine learning. So she has various different interests, but today I think she will talk more about the graph coloring. And with that, without further ado, I'll give the floor to research and to Mahsa.
Yeah, thank you, dear Daniela, for introducing me. Okay, thank you everyone for joining this meeting. I'd like to talk about vertex path cover of graphs. And it's not working. The concepts I'm going to talk about are graph definition, graph covering, and graph coloring of graphs. Well, first of all, let's see what a graph is. A graph is a set of nodes, we call them vertices, which are connected together with some lines, or we call them edges. So we can have some vertices with any connection as a graph, like this graph, or we can have some connection or edges between some vertices of the graph. Well, in graph theory, we have some problems named extremal problems. In these problems, we have a parameter, and we're looking for some upper bounds or some lower bounds on that parameter. So extremal problems in graph theory means how big or how small a parameter can be under some constraint. Well, graph covering and graph coloring is two of those problems I'm working on. Well, actually, my research project as a Herz fellow in Constant University is on covering of graphs. One of them is vertex covering, which is one type of covering of graphs. In these problems, we're looking for some minimum number of vertices that can cover each edge of the graph. It means that each edge of the graph has an end vertex in that set. As an example, you can see in the left side a graph with 7 vertices and 7 edges. We're looking for some minimum number of vertices that can cover each edge of G. If you consider 4 vertices, V1, V4, V5, and V6, you can see that each edge has an end vertex in this set. So we cover all edges with these vertices. Well, as an application of vertex covering of graphs, you can consider the edges of a graph as rows and all vertices as crossroads. Our aim is placing some security cameras at these crossroads to enable us see the whole city. And we want to use minimum number of security cameras in order to minimum all costs. So this is one of the application of vertex covering. But each problem in the graph theory, you can generalize it, and a generalization of a vertex covering is vertex K-path covering. Well, in vertex covering, we were looking for some vertices that cover each edge of G, and each edge is a path of length 1. So in vertex K-path cover, we are looking for minimum number of vertices in a graph that can cover all paths of length K-1. Similar to previous figure, we have again in the graph G with 7 vertices and 7 edges in the left side. And we're looking for minimum number of vertices that can cover each path of length 2. If you consider 3 vertices, V3, V4, and V5, you can see that we cover all paths like these red paths with 2 edges. And if you look at the induced subgraph on 4 vertices, V1, V2, V6, and V7, you can see there is no path of length 2 in these, between these vertices. So we can say that we cover the graph in the left side with just 3 vertices. Vertex K-path cover has a similar application like vertex cover. We want to suppose that we have a city and we want to equip the city with some facilities like gas stations or I don't know, security cameras or something like that. Although in these problems, we want to have one of these facilities in every L kilometers. The aim here is again using minimum number of these facilities or in order to minimum the cost. Well, till now, some researchers investigated this problem, and they have some results on cycles, trees, forests, and also they proved that for any graph G, the K-path vertex cover of the graph is between these 2 numbers. So they found a lower bound and upper bound for that. The lower bound is obtained by just counting the number of edges by considering a cover set, an arbitrary cover set. And the upper bound is by eliminating some vertices in a forest in a graph. Well, our aim is investigating the vertex K-path cover of some spatial graphs, and also we're going to find better bounds for any graph G. Well, so far we proved that for any Kneser graph of n and 2, when we have some restrictions on the number of on n as a parameter for Kneser graph, we find out that the K-path vertex cover of all of these graphs is equal to this number. It is less than the upper bound other researchers found out. And we are looking for other types of figures. Actually, when n is less than this number in the conjecture, we have some ideas that it should be again have the same value, except some cases when, for example, k is 4, we're looking for path of length 3. If we look at Kneser graph of 5 and 2, we can cover the graph with minimum number of vertices. I mean, minimum number of vertices in this equation. And for when k is 6 and n is 5 equal to 5, also we have the same result. But we are not just thinking on this problem. We are thinking on graph coloring because we think there's a relation between graph coloring and graph covering of graphs. And if we can find out this relation, maybe we can use graph coloring to find better bonds. Well, but what a graph coloring is? Graph coloring or a graph labeling of graphs is assigning some numbers or colors to elements of the graph. We have different types of graph coloring. Two of them, most important is vertex coloring and edge coloring. Well, in the left side, in figure above, you can see a vertex coloring of a graph. We color the vertices of the graph with 3 colors in a way that any 2 adjacent vertices, like these vertices which are connected together, have different colors. And in edge coloring, in figure below, we color the edges of the graph in which any 2 adjacent edges, means 2 edges that have a common vertex, have different colors. But we find out a relationship between star coloring and graph covering of graphs. A star coloring is a type of vertex coloring. So we are coloring the vertices of the graph such that, first of all, any 2 adjacent vertices have different colors. Second of all, there is no path of length tree in G, which is bicolor. It means that if you consider an induced subgraph on 2 color classes, like 2 color classes, green and yellow, you can see that there is no path of length tree with these 2 colors. But what is the relationship between this coloring and covering of graphs? If you eliminate vertices of 2 color classes, those color classes that have the maximum number of vertices, you can see that other vertices in the graph can be a cover set for the graph. So the vertex k-path cover is at most this one. And there are some problems I will talk about later that we are thinking of. The other coloring is defective coloring that has some connections with covering of graphs. In KD defective coloring, we are using K colors to color the vertices of the graph, but under some restrictions. And our aim is coloring the vertices of the graph in a way that any color class is an induced subgraph with maximum degree 2. So in this graph, which is a Petersen graph, we are coloring the vertices of the graph with just 2 colors. And as you can see, in each color class, like the induced subgraph on just green vertices, we have a subgraph with maximum degree 2. So we can say that this is a 2 and 2 defective coloring for Petersen graph. And the connection between this type of coloring and covering is that if, again, we eliminate all vertices of the biggest color class and add just some of them to the cover set to other vertices, we have a cover set for the graph. The problems we are thinking on, first of all, is finding some classes of graph with maximum degree delta for which the star coloring is at most delta. If we find these types of classes, actually we are able to better previous upper bounds. And the other one is finding some classes of graphs that the number of vertices in the biggest color class is is actually larger than the biggest forest in a graph that we don't know this parameter for any graph G. And the other one is finding the k-path vertex cover of bipartite graph. The last one is, I think it's a good question. As we, in previous upper bounds, they eliminate a forest in a graph. So when they eliminate a forest, they are actually eliminating or deleting lots of vertices from. They're putting lots of vertices in the set cover. But our aim is, instead of deleting vertices of a forest, deleting a bipartite graph from a forest, because in a bipartite graph we have lots of cycles, and we think that in this level we have better bounds for this vertex k-path cover. Yeah, I'm over, but I think I.
Okay, brilliant. So then I would also like to welcome Anteneh. Anteneh is our ZUKO fellow and joined us here also for 4 months at the ZUKO colleague and is back to Ethiopia now. He's a lecturer at Gebrie University in Ethiopia, but has gotten his PhD from Thailand. So he moved from very warm climate to us to stay with us for 4 months and work with Stefan Volkmann on different optimization strategies, but he will tell you more in a second. Anteneh has published widely already in his field, and more than that, he's already also has been awarded a Best Teacher Award at his university some time back. And he's looking at nonlinear analysis, optimization theory, and he shares an interest or passion with Mahsa on machine-based learning. And so we will have some more insights into mathematics in a second. And with that, I open the floor to Anteneh.
Okay, thank you for your introduction, Daniela. My presentation will be distributed accelerated algorithm for hierarchical optimization problem. Actually, the one which I submitted as a title was decentralized, but on discussion with my professor, better to make it from decentralized to distributed. Actually, distributed system is a decentralized, so maybe I changed this one to make it sharp and to explain the topic exactly. So I'm Anteneh. I was at University of Constance for 4 months as we conduct fellowship, and there is a host of Professor Stephen Walkin. My presentation will be on distributed accelerated algorithm for hierarchical optimization problem. Hierarchical means it's a bi-level problem. We're going to solve 2 problems at the same time. But the first, we have 2 layers of problems. So the first layer problem depends on the solution of the second layer problem. But we have a kind of optimization problem. So going to the outline of my presentation, I will start with introduction. Then actually we have a result in Wednesday for 4 months. We have got a result, and we have also have a preliminary numerical result of testing our result, and we have also a conclusion. This result is going to be, it's about to be submitted and somewhere in the journal. It's a matter of adjusting and preparing the manuscript. So let me start from introduction part. I want to start with why we make it distributed manner, or what is distributed method of solving optimization problem. So in the general framework, a certain system either works in a centralized form, or in a decentralized form, or in a distributed form. These are the 3 general parts of systems where a certain system is assumed to work, either it is centralized or decentralized or distributed system. So our system is distributed. So what's the difference between these 3? So this is kind of Mahsa's presentation. It looks like that, but it will explain exactly what is centralized and decentralized and distributed system. Centralized system is, we have a nodes. Here we can have nodes. So the information exchange between these 2 nodes passes through only exactly one center. They have exactly one center. So these nodes or these users have one center, and this center is connected to every user. So then every information passes through from one node to another node, passes through exactly one center, which is this center is common to all these nodes. This is centralized. So the information exchange is centralized here. Another one is decentralized. Decentralized is a little weaker than centralized. So here in a decentralized form, we don't have one center, but we maybe have more than two centers. Here, as we can see, different centers we have. It is still decentralized, but the center is not only one. We have more than one center in the information exchange of users, or in the information exchange of nodes or users, maybe. So the distributed system is different. The distributed system, you don't have even a single user, a single center. So each user is connected freely to every center, every node. So every user or every node has equal role of decision making here, equal role of decision making. So our system is kind of this. Our discussion of developing algorithm is developed so that there is no kind of center which is controlling the information exchange between nodes. So every part or every entry or every user has equal role of information exchange or equal role of is the outcome of the system, equal role. So distributed system is this one. But why we make it this distributed? Several settings in application do not fit themselves in a centralized manner. Not centralized. Not centralized means either it is decentralized or distributed. And it may be either decentralized or distributed system. So if it is not centralized, why we make it distributed is if the non-centralized systems most of them are distributed systems. The non-centralized situations arising in a real-life application takes the form of distributed system. And several problems in applications are modeled as a generic optimization problem of this one. So the motivations comes from this one. The motivation comes from this one. So several problems are modeled kind of this, and several problems are modeled in kind of this, and they are distributed. And they are in a distributed, they are working in a distributed form. So we have here users, GI and PI, minimizing this function, which is given as sum of some certain function, subject to X, an element of certain problem. Here we have a subproblem. This is minimized subject to this problem. So we have to solve this problem, and we have a set of points solving this one. So among the set of points solving this one, what is the minimum value of this function, where it is given as a sum of this function, where it is given as a sum of function? This is a bi-level problem or a hierarchical problem. So motivated by two very recent problems, very recent results, which are published in high impact factor journals, we are going to consider the problem, this one, where this function is given as a sum of m functions, but still this function GI is given as a sum of non-smooth function plus smooth function. In this paper, this problem is solved so that this function is only smooth. Here. This is whenever it is smooth. And in this paper, it is solved that this function is only non-smooth. So how about if one function is a sum of combination of smooth and non-smooth? This is our problem. And it's not only developing the algorithm, but we have to, our intention is just making the algorithm to converge faster than the previously considered algorithms. We are going to have some kind of effect on the algorithm, some kind of additional step, so that the algorithm is going to have a faster convergence rate. So the problem is this one. This function, the sum of smooth and non-smooth, and the subproblem is fixed point problem. This is a particular case. This problem generalizes several problems because in optimization, because optimization problems can be studied as fixed point problem. So this is a problem also considers whenever these problems are optimization problems. So my problem under consideration is a multi-agent constraint optimization problem of this one. So our agent is, for each I, we have Fi plus Hi and Ti. So the agents are Fi plus Hi, that is Fi, Hi, and Ti are kind of F1, H1, T1 is one node, F2, H2, T2 is another node. So you assume you have M nodes. So these nodes have equal contribution in decision making of solving this problem. So this is what we are going to make consider and what we are going to have as a discussion. So the problem, when we write the problem, when we rewrite the problem, it is kind of this problem. So our objective is to form distributed method for this multi-agent optimization problem. So, and investigate a unified accelerated iterative algorithm. And its implementation and convergence is significantly better, both theoretically and practical, using Polyak's heavy bore method. We are going to use this term so that the algorithm is assumed to have a better convergence rate, both theoretically and practically. So our problem under consideration is this one. So let's come to the result. Going to the result. So as I said, our problem, when we write our problem, is kind of this. And what are our assumptions given on Fi, Hi, and Ti? Fi, as I said, it is non-smooth function, which is continuous, convex, and its domain Fi is whole space H. And the proximal of Fi can be effectively computed on H throughout its domain. Let's assume this. Another is Hi. Hi is French differentiable. Its gradient is 1 over Li Lipschitz continuous. Fi is non-smooth, satisfying this condition. This is smooth, satisfying this condition. Lipschitz differentiable, 1 over Li Lipschitz continuous function. And the mapping Ti is Fermi non-expansive mapping. Fermi non-expansive mapping. So why it's good to make Fermi non-expansive, because this also solves this optimization problems. Because if it is non-smooth, proximal mapping is Fermi non-expansive mapping. So I can make this problem to be optimization problem. That's why I say that this is a generalization of several optimization problems, as optimization problems can be studied as a fixed point problem of certain nonlinear mapping. So as an assumption, S, the subproblem, is non-empty. Let's assume that the fixed point problem of this Fermi non-expansive mapping, the intersection, this set is non-empty. And let's assume that the minimizer among this S, the minimizer point of f of x among this set S, in this set S, the minimum point x bar in S, so that phi of x bar is the minimum of any value of x in S is non-empty. Let's also assume that this is also happening. So under these four assumptions, we are going to have a decentralized algorithm. So when we assume that an algorithm, we usually assume that we have parameters which we can control and which we can fix. And these control parameters, or these parameters, may have a convergence, an effect on the convergence rate. So let's assume that theta, lambda, and beta, and alpha n are decreasing real sequences converging to zero, satisfying this condition. This lies in this interval. This lies in this interval where Li, as I said, 1 over Li is the Lipschitz constant coefficient of each, the gradient of Hi, as I said. And Bi is between 0 and 1. Alpha n is between 0 and 1, including 1. Satisfying these conditions. We can have plenty of parameters satisfying this condition. the sum is infinite, and this limit is 0, this limit is 0, again, this ratio is 0. These 7 conditions. We can have parameters satisfying these 7 conditions. So our aim is 2 new class of accelerated proximal conjugate gradient algorithms will be developed for the problem under consideration using the pattern of incremental and parallel competition. This incremental type and parallel competition form of decentralized algorithm using the combination of proximal conjugate gradient and Halpern method. The proximal is we use the competition of the proximal for Fi, we use the gradient competition for Hi, and we use Halpern method for the proximal, the Fermi-Linian expansive Ti. And as an acceleration of the convergence, we use Polyak heavy ball method, which they call it in physics momentum acceleration method, which is adding this term. So our first algorithm is this one, distributed accelerated incremental algorithm. This is incremental type of algorithm. This is incremental type of algorithm. In algorithm, we have initialization, either it is we have to have initialization, which is initial guess of the solution of the problem. You guess the solution of the problem, and this iteration is going to make it very close to its solution. Your guess may be any point in H, so you start from a certain guess as x1, and when the iteration is increasing, x2, x3, x4, this sequence is getting close to its solution. So we have to give the initialization as x1 in this case. Or maybe we have also another initialization because this algorithm needs another initialization points in H. And D1 is equals to the gradient of HI, W naught I for each I. And we use the following step. Take this one as x1 because x1 is W11 because as we said, we have initialization and we have inner loop. Here, this is a finite loop. This is a finite loop. The inner loop is finite loop because it will terminate whenever I is equals to n. This is the inertial term, the Polyak effect. We have the proximal, which we can compute at Fi, and we have a gradient here, this competition, and here we have Halpern competition here. This loop is finite loop. It will terminate at m, and it goes when it reaches when it is less than m. We start with 1, 2, 3. When it reaches m, it will give the information to this one. Then this to this one. Then this is infinite loop, but this inside is a finite loop. At each iteration, we have a finite loop inside. Sorry. So this algorithm, what is the result of this algorithm? The result of this algorithm is this theorem, which has a proof of around 7 to 8 pages of proof of solving, showing that the sequence which is generated by this algorithm have the following properties. The lim suit of phi of xn is less than or equal to phi of x bar for all x in S. Every weak sequential cluster point of xn belongs to the solution of the bilevel problem or the radical problem. Any weak sequential cluster point. Okay. If phi is strictly convex, we have a unique minimizer. Connecting it with this one, we can show that xn weakly converges to P in the solution. So this is the result we obtained proving this theorem. The second algorithm is this one, this is the parallel competition. Each Fi, Hi is computed parallelly, Nti parallelly, and this parallelly computed values will be collected by this sum. We have m values at each loop here, and these m values will be collected at xn plus 1. This is infinite loop. What's different here is this is parallel form. The previous one is incremental form. So the same result we have in the mode of the distributed system is different, but we have the same result. Actually, we can have also different result for the previous algorithm 1. But this is a common concept of these two algorithms. We have the same result as we discussed for algorithm 1. So let's come to the numerical result of this algorithm, preliminary numerical result. So just as a test of our numerical result, we considered this minimization problem, and this is the indicator function, and this is a Euclidean norm, norm square, which is an Euclidean norm considered in a finite dimensional space in R3. This is the indicator function. This is non-smooth, and assuming that this is smooth one, the proximal can be computed. Actually, for this indicator function, the proximal is a projection mapping. The proximal operator is a projection mapping. So we tested our result for this simple example. So what am I going to show in here with this simple example is what is the effect of the parameters and what is the effect of the inertial term, or the inertial term in our algorithm. So after giving it some certain parameters for the algorithm in computing this problem, we have got this. This is coded by MATLAB. We have got this. This is for algorithm 1. These two results for algorithm 1. I don't think it is black. Maybe you can see it. For algorithm 1, here I cannot display everything here because A has its own value in my manuscript. But here theta n is 0. As you said, as you remember, in the algorithm, the inertial term is xn plus theta n in the bracket xn minus 1. Theta, if theta n is 0, the inertial term is removed. The inertial term. So if I remove the inertial term in this algorithm, as you can see, this blue dotted line, so it means that it has a slower convergence rate. The same is showing here. It has a slower convergence rate. But if I increase the parameter, as you can see, it has a very good convergence rate. This is the error. That is maybe it is the distance between two terms, xn minus 1. The norm of the Euclidean norm of xn minus 1. So this result is showing me that the inertial term has its own effect on the convergence of the proposed algorithm. Here also, in the second algorithm, you can see the effect of theta n when theta n is 0. So it has, as you can see here, the blue in the algorithm 2, it has a slower convergence rate. Based on this numerical algorithm, we say that the inertial effect has the inertial term has an effect on the convergence of the proposed algorithm, and the parameters have also effect on the convergence of the algorithm, because as you can see, for this value and for this value, the convergence is different. So this is the result we have as a preliminary result. I also tried to consider this one, but I'm not displaying it. But this, I consider this one for comparison of our algorithm with different algorithms from the algorithms of the papers which we took as a reference. I can have this 8 terms, so I can rearrange it and I can make it 4, because I can have combinations of 2. combinations of 2fi plus hi, so that this is quadratic function. And it is convex because H is symmetric and positive definite 5 by 5 matrix. So I also considered, we also considered as a numerical result this problem, but we use this one for comparison. I put this as we have different kinds of problems satisfying the conditions, and we can formulate a problem which is equivalent to our problem of consideration. So the last one is our conclusion. Based on our result not only improve and generalize several known results in literature, and also provide a unified framework of studying other problems related to 1 and 2. Our problem generalizes several known problems in literature. That's what we see. And our numerical experiment displays that the efficiency and the potential practical application of our algorithm. And the numerical also result displayed the benefit of the inertial extrapolation, or the inertial term in the acceleration of the proposed terms, as you said, as you can see, if theta is 0, it has a low rate of convergence. So this is the conclusion that we drawn from our result. Thank you very much for listening. Thank you.
I think with these words, we may close the session, because as it seems like math will solve all our problems, will optimize everything, or at least this is what I hope for. And so for my thing, I think there's no more questions, and maybe people can be in touch later on. And I was wonderful to see you, Mahsa and Anteneh, again. I hope to see you also at the Vertexes, because you will stay with us digitally still a while longer.